Hello and welcome to our physical sciences session. My name is Themba Ncube. Today we are focusing our attention on the revision of stoichiometric problems. We'll address a number of different questions ranging from the multiple choice as well as structured questions. So now this is the concept map in as far as quantitative aspects of chemical change, right? So you'd realize that it covers a broad aspects of of chemical change, and the questions on stoichiometry can be on any of the concepts as long as there is a chemical reaction. It could be on limiting reagents, yield, purity, it could talk about percentage composition, So just pay attention to the fact that a stoichiometric problem can be asked in whichever, context of chemistry, right? And the most important thing that we also need to remind ourselves is the data sheet, right? So the data sheet forms, a most important part of our information sheet in terms of responding to questions. So familiarize yourselves with the data sheet and be able to identify the correct formula. The general rule is that we do not change the subject. We copy the formula as it is, and then try and isolate the unknown as part of our responding to questions, right? So the mole concept is broad and it covers a number of aspects. It could be with respect to the Avogadro number, right? It could be, in terms of molar gas volume at STP. So we need to qualify that at standard temperature and pressure, that a mole of any gas occupies a fixed volume. It could be on concentration, So the two formulae can be used, one after the other, or the second part is actually a combination of the mole calculation and the concentration to give us the formula C is equals to M over MV, right? Let's look at multiple choice. You are given 4 options, but what is important in as far as the multiple choice question is to read the question with an intention to understand without even looking at the given options. In the case that you get stuck, you can also do the elimination as part of identifying the most correct response. So this question says 10 moles of hydrogen gas and 2.5 moles of nitrogen gas. Okay, these are the two reactants. They are allowed to react to form ammonia according to the following balanced equation of reaction. So the equation of reaction, what does it tell us? It tells us that this is the stoichiometric ratio in which these substances actually react with each other, right? So pay attention. The mole is the SI unit of quantity of matter. So we don't talk mass, we don't talk volume, we talk about a mole. Because why? A mole of any substance has the same or constant number of particles. Whatever the particles could be, it could be the mole, it could be the ions, it could be the atoms, it could be molecules. So we always talk about the mole, right? So in this case, we are given the quantities in SI unit. Okay, so 3 moles of hydrogen reacts with a mole of nitrogen to give us 2 moles of ammonia. So we are told that if 4 moles of ammonia are formed during the reaction, what are the remaining moles of the reactants, right? So we want to know that after forming 4 moles of ammonia, how much will be left in terms of the hydrogen and the nitrogen, right? Okay, so we know that if we have got 4 moles of ammonia that are formed. Okay, to form 4 moles, how many moles of nitrogen are needed? If 1 forms 2. So to form 4 moles, we would need, so our ratio, right? Our ratio is 3:1:2. So for us to form 4 moles, how many moles do we need? We need half that number, which is 2. So initially, what we have, we've got 10 moles, right? And 2.5 moles, right? Okay, and then we had nothing there, okay? Now, if the change in moles that we get here, in this case, if we started with 2.5 moles and 2 of them reacted, how much of nitrogen is left? 0.5 mole, okay? Right? Okay, and then for us to to react the 2 moles, if the ratio of nitrogen to hydrogen is 1:3, so if we reacted 2, we need 3 times as much of hydrogen as nitrogen. So what do we have here? We have 6, right? Because 2 times 3 gives us 6. So if we started with 10, okay, the remaining will be 4 if we reacted 6, okay? So this is what remains for hydrogen and for nitrogen. So if we go to our solutions, okay, we know that we'll be left with 4 of hydrogen, okay? So the option is between C and D. But for us to eliminate the correct one, we would know that for ammonia, actually for nitrogen, we're left with 0.5. So this becomes the correct answer. So these other options are totally out. Then our correct option becomes option C, right? And then in the next question, we have a solution that will have the greatest concentration of hydrogen ions when complete ionization occurs. So what do we have here? We've got sulfuric acid. For every mole of sulfuric acid, right, we actually get double the number of moles of hydrogen ions, okay? And the sulfate, 1. So the ratio is 2:1 in terms of the product. But as far as HCl, what do we have? We have got 1 produces 1 mole of HCl, ionizes to give us what? 1 mole of hydrogen ion, okay? Right, and then, so in this case, this one, sulfuric acid becomes a diprotic, while hydrochloric becomes a monoprotic. But then also we have another one. This ethanoic acid, CH3COOH, will also give us 1 for every mole that dissociates, okay? So we need to pay attention to that. So here, if we want a higher concentration, we'll look at these options because it says the greatest of them all. So we need the one that will have, the greatest. So 0.4, if it dissociates, it will give us double 0.4, which is 0.8, right? Okay, so this one will give us what? 0.8 mole per cubic decimeter, right? While the second one will give us the same 0.4, okay? Okay, mole per cubic decimeter of the ion. The second one will also give us, if we've got 1 cubic decimeter, well, that's the volume, okay? So if we look at the second one, which says 0.4 moles of that. So if that's the volume, okay, we know that concentration is equals to number of moles over volume, okay? So we'll try and actually get as to which one has got a greater concentration. But if you realize that this gives us double the number of moles, so obviously that's what we pay attention to. So our option in that case will eliminate in the process, and at the end of the day we'll make a comparison in terms of the quantities, right? So, and as far as multiple choice is concerned, what is very important is that you read the question carefully before you answer, and also try and eliminate. It's not a simple guesswork. So that's as far as the multiple choice, as an example of stoichiometric problems, okay? Well, that's it for now. We shall take a short break for now, and then we'll come back and do more problems. Welcome back. We're still focusing our attention on more stoichiometric problems and try to understand some of the important things that we have to take note in as far as sharpening our skills of responding to stoichiometric problem. And it's also very important to note that the questions on stoichiometry can be asked on any topic as long as it involves a chemical reaction. Now let's look at one more example in terms of these questions on stoichiometry. Right. Okay. Now we have got 40 grams of iron metal and 35 grams of chlorine. Okay. These are the quantities in terms of mass that are given. These two, they react to form iron 3 chloride. Very, very important in terms of chemical formula. Iron 3, because iron is a transition metal, it simply says to us that in this ionic compound, iron has an oxidation number of 3+, okay? Right, but the balanced equation of reaction is already given to us. It says 4 moles of iron reacts with 3 moles of chlorine, right, to give us 2 moles of iron 3 chloride, right? So what does this tell us? It tells us that the stoichiometric ratio in which these substances participate in this chemical change is 4:3:2, right? Now the first question, define, that's the action verb, right? So in as far as definitions are concerned, we need to be very, very specific and pay attention to the key words. So our examination guidelines are our point of reference in as far as remembering definitions. We must capture the key words in the correct context. And also remember that in as far as definitions, because it's just about remembering. So it's either you get the full 2 marks or nothing. So you need to practice our definition always. These are our quick wins. These are our easy marks in as far as questions are concerned, right? So the definition of the term limiting reagent. Okay, what is a limiting reagent? This is the substance, okay, the reactant, okay, whose quantity, okay, or whose amount, okay, determines the amount of product obtained. Of product in a reaction, okay? So in other words, we are saying that this is the substance or the reactant that gets used up. So the amount of product that is obtained in a chemical reaction depends on the quantity of the limiting reagent, okay? Now the follow-up question says, calculate which of the reactants will be used up in the reaction, right? Okay, so the one that is going to be used up, in other words, we would rephrase the question and say, what is it that the question demands of us? It actually wants us to identify by means of calculations, that is, the substance that is a limiting reagent, okay? Right, so this is a stoichiometric calculation. What are we given? We are given masses, right? But then what is the SI unit of quantity of matter in a chemical reaction? We talk about the mole. Now, let's check, because we've got the stoichiometric ratio of 4:3:2, okay? Now, we are paying our attention on the reactants because we want the limiting reagent. So we can safely classify this question under limiting reagent, okay? So it's all about the limiting reagent, okay? So we're going to do a couple of calculations for us to arrive at that. So the stoichiometric ratio is there from the balanced equation. Now the next thing that we ask ourselves is how many moles are there for each of the sample of substance of the reactants, right? So we know that the number of moles, the moles of iron rather, okay, is equals to mass of sample over molar mass, right? What's the mass of iron sample that is given? It's 40 grams, right? Divided by the molar mass, which is 56, right? So let's calculate the moles of iron in this case. So the moles is going to be 40 grams divided by 56 grams per mole. That gives us, as a decimal fraction, 0.71 moles, okay? So this is equals to 0.71 mole, okay? What about the moles of chlorine that we have? So the moles present for chlorine, which is a diatomic, molecule, is equals to mass of the sample over the molar mass, okay? The given mass of the sample is 35 grams, right? Divided by the molar mass, which is 2 multiplied by 35.5, right? So if we go to our calculator, what do we get? We'll have 35, okay, divided by 2 multiplied by 35.5, okay? Right, close that bracket. Okay, this gives us a value of 0.49 moles, right? So there's 0.49 moles of chlorine, right? Now, let's ask ourselves an important question. Let's say, for argument's sake, we know that for every 4 moles of iron, there should be 3 moles of chlorine, right? So if we say, for argument's sake, if let's say all the iron has to react, the ratio of iron to chlorine gas is actually 4:3, right? So 4:3. Now let's say assume that the entire 0.71 moles reacts. How much of chlorine do we need? Let's say that is X, all right? So by simple calculation, the X in this case becomes 3 multiplied by 0.71 by cross multiplication over 4, right? All right, then we can evaluate that and try and decide if indeed all the iron will react. And when we say all the iron reacts, we are saying, in other words, iron we are just checking by trial and error, is iron our limiting reagent or not? Okay, so what do we have there from the calculator? We get 3 multiplied by 0.71, right, divided by 4. Okay, what does that give us? It gives us 0.5, right? Now, in other words, for all the iron to react, we need 0.53. But how much of chlorine do we have? We've got 0.49. Then it means all the iron will not react because we can't have 0.53 of 0.49 reacting. In other words, we have less of chlorine. Now, let's do it the other way around and use the same ratio of 4:3, all right? Let's say all the chlorine reacts. Okay, how much of chlorine do we have? 0.49, right? And then how much for 0.49, how much of iron do we need, right? So it's still the same ratio, iron is to chlorine, okay? Right, so by simple calculation, our X becomes, we cross multiply 4 multiplied by 0.49, right, over 3, okay? So if we can check that on our calculator, what do we have? We have got 4 multiplied by 0.49 divided by 3, okay? Right, our answer is as a decimal fraction is 0.65. Now, what are we saying? We are saying X, okay, if you can go back to that, okay, we are saying X is equals to 0.65 moles, right? Now, what are we saying? We are saying that if all the 0.49 of chlorine reacts, how much of iron is needed? It's 0.65. Already, how much of iron did we have? We've got 0.71. It means all the chlorine will react, and some of this 0.71 moles will actually react, and some of it will be left. So, in other words, we are saying that chlorine is our limiting reagent. So, therefore, we are saying chlorine gas is the limiting reagent, right? If chlorine is the limiting reagent, what does it say by implication? We are saying that iron is the one that is in excess because of the 0.71, only 0.65 moles of iron will react based on the stoichiometric ratio, right? Okay. Then the follow-up question says, how many grams of the other reactants are in excess? Very important question, right? We had, because iron, okay, is in excess, okay? Not all the iron actually reacts, okay? So the remain unreacted moles, okay, of iron, okay, of iron is equals to actually what we started with, 0.71 less 0.65. If you can quickly go back and confirm, because what actually reacts is 0.65, right? So 0.65 moles. So how many moles are there? We can quickly verify that and say, okay, we started with 0.71. Of that 0.71, only 0.65 of it reacted, okay? We need to subtract that. 0.65. So how much is unreacted? As a decimal fraction, 0.06, right? So only 0.06 moles are unreacted. But the question says, how many grams? So the moment it says grams, we are interested in which quantity? The mass unreacted, okay? So mass that is unreacted will change these moles back to the mass. So we know that moles of substance is mass over molar mass. But here, what are we talking about? We're talking about iron because it is in excess, right? Now, the moles is 0.606 that is unreacted, okay, is equals to whatever mass we're looking for over 56. So the unreacted mass is actually that product, right? So we have 0.06 multiplied by the molar mass of iron, which is 56. This gives us, as a decimal fraction, 3.36 grams, right? So 3.36 grams of iron is unreacted, okay? So that's the main idea in as far as the stoichiometric calculation. So if we say from the ratio of 4:3, right, and then all of the chlorine reacts, it means chlorine is the limiting reagent, which will determine the amount of iron 3 chloride that will be formed. So if chlorine is the limiting reagent, it tells us that iron is the one that is in excess. So in terms of language, let's pay attention to that. We understand that a limiting reagent gets used up, okay? And once that limiting reagent has been used up, what essentially happens, the reaction stops. And then we would say that the reaction has reached completion. Okay? And then for the other substance that is not a limiting reagent, we'll describe it in terms of the substance being in excess. Then we always work in moles because that's the SI unit of quantity of matter. So we can change the unreacted moles to actually determine the mass that remains in terms of the excess substance. Okay, right. So these are some of the ideas that are very important, right? Okay, now the last follow-up question says, how many iron 3 ions are present in the product, right? So in terms of the moles, we know that 4 of iron forms 2 moles of the iron 3 chloride, okay? And then 3 of chlorine actually form 2. Okay, it's a very interesting question because we're talking about the number of ions. So this has got to do with the Avogadro number of substances, okay, of particles of a substance based on the mole concept. So how much of iron 2 is formed? Iron 3 chloride is formed. That's the question that we want to ask ourselves. How many moles will be formed? Okay, so 4 of iron forms 2. So the ratio of iron to iron 3 chloride, okay, which is Fe2Cl3, is the ratio is 4 produces 2, right? So how many moles of iron did react? We said 0.65, okay, moles. So 0.65 will form half that because 4 forms 2. 0.65 will form half that. So if we go to our calculator once again, we'll say 0.65 divided by 2, okay? This gives us, as a decimal fraction, 0.325, okay? So this will be 0.325 moles, okay? Right, but then if we go back to this equation in terms of per formula unit, what do we have? We have got Fe, okay, 2Cl3, right? So in terms of ions, it will be 2Fe, okay, 3 plus, right? And plus 3Cl minus. So for every mole of iron 3 chloride, there is double the number of moles of iron. So if we have got 0.325, okay, moles, it will form 2 times that, which is 0.325, okay? Right, so this is the actual number of ions of Fe3 plus, okay? But then we know that number of moles is equals to a number of particles divided by the Avogadro number, right? So we've got this, which is 2 multiplied by 0.325, right? Is equals to number, which is the FE, the number of particles, then divided by 6.02 times 10 exponent 23, which is the Avogadro number, right? So the number of particles is actually a product of that, okay? So if that's the case, we would go to our calculator, okay? What does it give us? It's actually a product. We can isolate the number of particles, okay? So which means it's 2 multiplied by 0.325, okay? Times Avogadro number, which is 6.02 times, okay, times 10 exponent 23, okay, right? Then this gives us the number. So how many particles are there? So that number is actually 3.9 times 10 exponent 23, okay? 3.91 times 10 exponent 23. So this is the actual number of particles, okay? So, you know, the mole concept is quite broad, and the questions on stoichiometry can be on any topic. So it is about the mole, okay? So for now, we just want to try and say, okay, these are the main things, you know, in terms of the mole concept, but there is more. A lot of practice will actually boost our confidence in as far as this is concerned, right? We'll take a short break for now, and then after that, we'll continue with more revision on problems based on stoichiometry. Let's take a short breather for now. Now let's look at more questions in as far as stoichiometry revision is concerned. This question says 50 grams of butane, right? A butane is a hydrocarbon. It consists of carbon and hydrogen. So it is used as a fuel, and then it burns completely, right? It burns completely in excess oxygen to produce carbon dioxide and water. So if the question says, if the statement says it burns completely, it means all the butane actually is used up in the reaction, meaning butane is our limiting reagent, and then oxygen is in excess, because we are told that this combustion or this burning process takes place in excess oxygen to produce carbon dioxide and water. But just to put this context, you know, into context, let's understand that most hydrocarbons are actually used as, you know, fuels. They are a source of energy. What does that tell us? It tells us that when these fuels burn, the major product that we actually want to get from this fuel is energy. So this is typically an exothermic reaction, okay? So the carbon dioxide and water are actually the byproducts, okay? So because energy is not a chemical per se, would only include the byproducts in the reaction, right? And then the question says, calculate the volume of carbon dioxide, right? That will be produced at STP. What does STP stand for? It stands for standard temperature and pressure, right? Because this is a stoichiometric problem, it says that the law of conservation of mass must actually be applied. Now, let's ask ourselves the question, is the equation of reaction balanced or not? If not, then we need to do something about it. Okay, let's check carbon, okay? Carbon is 4 on the left, 1 on the right, okay? So then we need to do something. I'll be tempted to put a 4 there, okay? Then carbon is sorted. What about hydrogen? We've got 10 of hydrogen on the left and then 2. It means we'll need maybe a 5 there, okay? Then that leaves us with oxygen, right? Now, if you look at oxygen, on the left it's just 2, and then on the right we've got 4 times 2, which is 8, plus 5, which gives us 13, okay? But already, if it's 2 is to 13, and then this side will definitely need maybe a 13 over 2, okay? But remember, when we balance, we use integers or whole numbers. What does that say? We have to multiply everything by 2. so that we get rid of that denominator, which is the 2. So pay careful attention to that, right? So if we multiply everything by 2, we're left with 13 there, okay? Then we'll have 2 there. 4 times 2 here, we'll get 8, and then here we'll get 10, right? Now let's check if it is balanced indeed. Carbon, it's 8 on the left, 8 on the right. Hydrogen, 2 times 10, that gives us 20. We also have 20 on the right. Oxygen, we've got 13 times 2, which is 26. Now, if you go to the right, it's actually 16 plus 10, which gives us 26. So the stoichiometric ratio in which these substances react to form the product during this combustion reaction. So this burning completely, it's combustion, right? So the term that refers to the burning of fuels in excess oxygen is called combustion. So the stoichiometric ratio is 2 is to 13 is to 8 is to 10, right? Now we want to know what is the volume of carbon dioxide that will be produced at STP. This is a multi-step type of a question, okay? So the first part of the multi-step was to balance because the reaction equation for the reaction was not balanced. So we ask ourselves, how many moles are present in 50 grams of butane, right? So we know that moles of methane, so butane, which is C4H10, is actually equal to mass of sample over molar mass, all right? The sample is 50 grams divided by the molar mass of butane. So it's 12 times 4, all right? Which is 48 plus 10, which is 58, right? So just to verify that by means of a calculation. So carbon the mass of carbon is 12 multiplied by 4, right? Then we would add 10 for hydrogen, okay? Right? Plus 10, okay? That gives us a value of 58, right? That's 58 grams per mole, right? So if we calculate the moles that are present there, so it's going to be 50 divided by 58, okay? So in a 50 gram sample of butane, we've got 0.86 moles, right? So this is 0.86 mole, right? Okay, now we want the volume of carbon dioxide. So 2 moles of butane produce 8. So the ratio of butane to C4H10 to carbon dioxide is 2:8, right? So if we've got 0.86, okay, it will give us what? 4 times that. So if we're looking for 4 times that, it's going to be 4 multiplied by 0.86. Where am I getting the 4? Where are we getting the 4? If 2 produces 8, it means 1 will produce 4, okay? So that's, we get a decimal fraction of 3.44 moles, right? So this will produce 3.44 moles. Now we're asking ourselves that if the moles of carbon dioxide is equals to 3.44 moles, okay, what volume will be occupied by that number of moles of carbon dioxide? Okay, so what do we know? We know that a mole of any gas at standard temperature and pressure will actually occupy a fixed volume, which is the molar gas volume of 22.4, right? So we know that moles is equals to volume over molar gas volume, right? Now, for us to determine the volume of hydrogen gas, we'll then say 3.44 moles is equals to the volume that it will occupy divided by the molar gas volume, which is 22.4 cubic decimeters, right? So our volume is actually the product of the moles of carbon dioxide and the molar gas volume. So for us to get that, we can simply do our calculation, 3.44 multiplied by 22.4, which is a constant, right? Okay, this gives us a value of 77.06, right? 77.06 0.06 cubic decimeters, right? So that's the volume of carbon dioxide that will be formed. So what is important here is to recognize which aspect of the mole concept the question actually deals with. Thereafter, identify the correct formula, do the necessary substitution, but remember to convert the mass into mole. Why? Because the mole is the SI unit of quantity of matter. So this is typically your multi-step type of a problem. Hopefully that makes a lot of sense. Welcome back. We're still focusing our attention on, revising stoichiometric problems. So we've managed to look at, questions that involve multi-steps. Some are routine calculations, and we've indicated that if it's a routine calculation, it could be a 3-mark type of a question where you identify the correct formula without having to change the subject. You do the necessary substitution, pay attention to the SI unit, and then after that you get the correct answer, including the correct units. Then that could be usually a 3-mark kind of a problem. But if a calculation question has more than 3 marks, it may be an indication that it's a multi-step type of a problem. So just pay attention to the mark allocation as well. Now let's focus our attention on a different structured question, still on stoichiometry, right? A solution of potassium sulfate is prepared by dissolving 6 grams of potassium sulfate in 500 cubic centimeters of water. So what is important here? Potassium sulfate is completely soluble in water, so it dissolves completely. So it will form actually what we'd want to think of as a homogeneous solution, right? So once that happens, we know that all the potassium sulfate has dissolved because it's a group 1 salt. Right. Now, the question says calculate the concentration of potassium ion in the solution. Okay. Now, first of all, we need to determine the concentration of potassium sulfate first. Right. So, as far as the concentration in 6 grams, we would ask ourselves how many moles of potassium sulfate are present. So, the moles of potassium sulfate K2SO4 present is mass over the molar mass. Right. Now, the mass of this sample is 6 grams, right, divided by the molar mass. So if we go to our periodic table for potassium sulfate, we know that potassium is number element, it has got a mass of 39 grams per mole. So it's going to be 39 multiplied by 2, okay, plus sulfur, which is a mass of 32, there's only 1 of sulfur there, plus, and then oxygen, which is 16 times 4, right? Okay. What does this give us? It gives us 174 grams per mole. Okay. So that's the molar mass, 174 grams per mole. So how many moles are present in that? We are saying, okay, by way of calculation, we would say 6 divided by the molar mass, which is 174, right? Okay. What do we get? It gives us as a decimal fraction 0.034 moles, right? So this is 0.034 mole, right? Furthermore, we also know that in terms of concentration, we know that concentration is equals to moles per unit volume of solution. So what do we have here? We've got 0.034 moles, okay? 0.034 divided by the volume, but this volume is given in cubic centimeters, okay? So it's going to be 500 multiplied by 10 exponent minus 3. This is the conversion, because for every cubic decimeter, there is 1,000 cubic centimeters. So what's the concentration of potassium sulfate? Okay, we'll go to our calculator once more. Okay, we know that that's 0.034, okay, divided by 500 multiplied by 10 exponent negative 3, okay? Okay, if we can just put a bracket there so that it becomes very accurate. So you need to familiarize yourself with the use of the scientific calculator, okay? So the concentration as a decimal fraction is 0.068, right? So 0.068 mole per cubic decimeter, right? So what do we have here? The ionization or the dissociation of the potassium sulfate. For every mole of potassium sulfate, we get 2 moles of, the ratio is 1:2, 2 moles of potassium ion. So the concentration of potassium ions in this is equals to actually 2 multiplied by 0.068, okay? Then this gives us, if we can quickly calculate that, we'll get this, will multiply by 2, we double it, okay? Then this gives us, as a decimal fraction, 0.136, right? 0.136 mole per cubic decimeter, right? So that's as far as the question is concerned. Also, you may think of this as a multi-step type of a problem. And then let's shift our attention to a different scenario altogether. It says here calcium carbonate is a key component of eggshells. If it says it's a component, it means it's made of, the eggshells are made of calcium carbonate and other substances, okay, which is very important for skeletons, okay? And then a group of learners decided to determine the percentage composition of calcium carbonate in the shells at STP, standard temperature and pressure. So we've got 5 range sample of the shells which are crushed and reacted with hydrochloric acid according to the balanced equation of reaction. So the stoichiometric ratio in which they react, it's 1:2:1:1:1, right? That's very important. And then this reaction was also conducted at standard temperature and pressure. Now, wait a minute. The moment we see STP, we immediately think of the molar gas volume, that a mole of any gas at standard temperature and pressure would occupy a fixed volume, which is 22.4 cubic decimeter per mole, right? So that's in terms of the table of the physical constants, which is something that you need to familiarize yourself in as far as the formula sheet is concerned, right? So we are told that there is 1.06 cubic decimeters of carbon dioxide which was collected, okay? Now we would ask ourselves how many moles of carbon dioxide were actually formed, okay? Then we'd work backwards to determine the purity of calcium carbonate, right? Okay, so from this, we know that there's 1.06 that's the volume of the carbon dioxide gas that was collected. So in other words, we'll say moles of carbon, okay? Moles of carbon dioxide is equals to volume over molar gas volume. So that's the first part of this multi-step problem. So we can determine the actual moles of that. So we'll say number of moles of carbon dioxide is equals to, the volume is 1.06 divided by 22.4, which is the actual molar gas volume, okay? So we can quickly determine that. So that's 1.06, okay, divided by 22.4, which is the constant. So how many moles are there? 0.047, right? 0.047 moles, okay? Now, if we work backwards, we would ask ourselves that if 1 mole of carbon dioxide is produced by 1 mole of calcium carbonate, okay? It means how many moles of calcium carbonate are present. So the moles of calcium carbonate is actually equals to the same number of moles, because it's 1:1, is equals to 0.047 mole. Okay, this is based on the stoichiometric ratio, right? Now, I would also ask ourselves that, okay, what's the mass of 0.047 moles of calcium carbonate? We would know that, again, the moles of calcium carbonate is equal to, okay, the mass over the molar mass. Now, we also actually need to do that calculation, but we know that this is 0.047, And the mass of calcium carbonate is actually 100 grams per mole. You can verify that on the calculator. Then we want to ask ourselves, of the 5 gram sample, okay, what is the actual mass of calcium carbonate? Because remember, we said this calcium carbonate is contained in eggshells. It means there is calcium carbonate and some other substances. Then what's the mass of calcium carbonate that is present in that sample? So we'll go back, okay, and actually do that calculation on our calculator. What do we have? We're going to have 0.047, okay, multiplied by 100, okay. If we multiply that by 100, we get 4.7, right? Now, what is this 4.7 grams? Right, let's break this down and bring this into context. Now, the sample of the eggshell, the total mass is actually 5 grams. Now, of that 5 grams, only 4.7 grams is actually calcium carbonate. So in other words, we are saying that a major component of that eggshell consists of calcium carbonate, which is 4.7. Then it means the remainder thereof actually is the impurity. Okay, so we can, in a way, get to a point where we are able to determine the percentage purity, right? So how do we move from this? Now, this is the actual mass of calcium carbonate, right? Now, if we want to determine the percentage purity, we know that percentage purity, okay, that's the last part of our multi-step problem, is equals to mass of calcium carbonate in sample, okay, divided by total mass, okay, multiplied by 100, right? So in this case, what do we have? We have the total mass, the mass of the calcium carbonate that we've managed to calculate is 4.7 grams, okay, divided by the total mass of the sample, which is 5 grams, right? We multiply this by 100, okay? So if we go to our calculator, this is the easy part because we've done all the science. Now it's just the calculation that's left. What do we have? We have 4.7, okay, divided by the total mass of the sample, which is 5. We're going to multiply this by 100, okay? This gives us 94%, right? Okay, this gives us 94%, right? So now what does the 94% purity mean? It means of the 5 gram sample of the eggshell, what is actually calcium carbonate is 94%, and then the remainder is actually other substance that did not take part in the reaction in forming the carbon dioxide that we collected. So we need to practice these kind of problems, quite often so that you become more comfortable in them. So now we've managed to cover most of the important things about these stoichiometric calculations. So practice becomes very, very important. Everything of the best.